Okay, this is practice exam AB-3. I'm going to try to get in this video numbers 5 and number 6 done. So in number 5, they give you a slope field. And the first question says sketch the solution curve that passes through the point 0, -3, and then another one that passes through the point 0, 1. So what you do is you come here to 0 and -3 and you just follow the contour around. And they want you to sketch it right there on there. And then the other one is at 0, 1, and you would just follow the contour around. So try it on your paper. But if it were to look like this, right, and -3 is down here, then it would, if you follow the contour around, I don't know, it's going to look something like that. Okay, try it yourself. And then the one at that is up at 0, 1, okay, so that starts up here at a y value of 1. It's more of kind of a parabola look to it. But you just follow the slopes of the lines all around and just connect them together like that. Okay, so I hope you get one like that, because that one is not too hard at all. Alright, 5b says find the second derivative and explain why every point of inflection on the solution curve has a y-coordinate that is less than 0. Okay, so we have dy dx, back to the original part of the problem, is equal to x times y squared plus 1. Alright, so we want to find the second derivative. Alright, so this is a product rule. The first, x, times the derivative of the second, 2y, dy dx, plus the second, y squared plus 1, times the derivative of the first, x, that's just 1. So I would have 2xy dy dx plus y squared plus 1. So we can substitute, since dy dx is x times y squared plus 1, we can substitute that in and be 2x y times x times y squared plus 1. So again, that's just dy dx plus y squared plus 1. Alright, let's go ahead and multiply all that out. So that would be 2x squared, since there's a y squared plus 1 in both, it looks like we could just factor that out. We'd have 2x squared y, and if we factor out a y squared plus 1, then plus 1, so we'll factor out a y squared plus 1 out of both, and 2xyx would be 2x squared y, and then y squared plus 1. So hopefully you can tell what I did there. So at a point of inflection, right, at an inflection point, you know that the second derivative has to equal 0. So we have to set this equal to 0, and you know that part can never be 0, because no matter what you put in for y, if you square it's going to be positive in this plus 1, so never 0. So we know if we set the other part, 2x squared y plus 1 equal to 0, and we solve for y, then y is equal to minus 1 over 2x squared, and the bottom will always be positive, the top is always negative, so that is always less than 0. So that's your explanation of why y is always going to be negative at a point of inflection. Okay, so that's kind of a detailed problem. I would want you definitely to get the first part right to get this equation right for the second derivative. And the explanation is a little bit tough. Okay, so let's do part C. Says find the particular solution given f of 0 is equal to 1. So we're going to start back out with dy dx is equal to x times y squared plus 1. We're going to separate the variables, integrate both sides. We know our initial condition is f of 0 is equal to 1. Okay, let's separate the variables. We would have dy over y squared plus 1 is equal to x dx. Right, I brought that y squared plus 1 underneath the dy and then shot the dx over to the other side. We want to integrate both sides. Okay, so this one's a little tough. You have to recognize that's inverse tangent. Remember, it's 1 over the variable squared plus 1. That's inverse tangent of y. And that's going to be equal to 1/2 x squared plus c. We know that f of 0 is equal to 1, so we can get our value for c. So that's going to be plug those numbers in. Inverse tangent of 1 is equal to 1/2 times 0 squared. So that's just going to go to 0, the 1/2 x squared. And that's equal to c. So that's pi over 4. The angle whose tangent is 1 is pi over 4. So we would have inverse tangent of y is equal to 1/2 x squared plus pi over 4. That they might be good with that. You might be able to circle that. But if they make you solve for y, then what you would do to get rid of that inverse tangent is take the tangent of both sides. Right? Take the tangent of inverse tangent and you would just have y. And that's equal to the tangent of 1/2 x squared plus pi over 4. That's probably the safer way to do it, to go ahead and solve for y and not leave that inverse tangent in there. Okay, so that is a wrap on number 5. Let's see if I can get number 6 in here before my video camera shuts off. It shuts off at about 16 minutes. I think that's all the battery life I have, but I got new batteries coming from Amazon. So hopefully they will arrive and I can do longer videos with this particular camera. Alright, so number 6 says consider the ellipse. So we have x squared over 16 plus y squared over 9 is equal to 1. And then we have a hyperbola, x squared over 9 minus y squared over 16 is equal to 1. We want to find part A, dy dx of the ellipse. Okay, so that's this one right here. Okay, well, I think I can do that. So let's ddx that thing. Okay, so that's going to be 2. Bring the 2 out front. So 2x over 16 would give us just x over 8. Or let's call it, instead of x over 8, I'll do 1/8 x. Plus 2y over 9, or 2/9 y, is, and that'd be then dy dx, can't forget that, is equal to 0. Alright, solving for dy dx, I would have 2/9 y dy dx is equal to negative 1/8 x. Alright, so dy dx is equal to negative 1/8 x over 2/9 y. And then when you flip and multiply those fractions, you'll get negative 9x over 16y. Okay, so that would be the answer to part A. So that'll give you the slope at any point for that ellipse. Now we want to write an equation for the tangent line to the ellipse at 12 over 5, 12 over 5. Okay, so I'm going to want to keep that negative 9x over 16y handy. Okay, so if we've got a point 12 fifths, 12 fifths, excuse me, so we have y minus y1 is equal to the slope times x minus x1. Okay, so our slope m is going to be minus 9 times 12 fifths, just plug in that point for x, over 16 times 12 fifths. Well, notice the 12 fifths just cancel, and I got a negative 9 over 16. So we have y minus 12 fifths is equal to negative 9 sixteenths. Excuse me. Times x minus 12 fifths. Right, and that will do the trick. Made for easy math that those 12 fifths over 12 fifths canceled. Okay. Alright, so that is part B. Let's see if I can fit part C in here before this thing shuts off. So part C says find an expression for the slope at any point on the hyperbola. Alright, so we want to d dx, that value, so that's going to be 2/9 x minus 2y over 16 would be 1/8 y, dy dx is equal to 0. So I've got minus 1/8 y, dy dx is equal to minus 2/9 x. So dy dx is equal to minus 2/9 x over minus 1/8 y. After flipping and multiplying, so we'd have, after we flip, we'd have an 8 times 2 and then a 9 times 1. So I'd have 16x, the negatives will cancel, over 9y. And that'll give me the slope anywhere on the hyperbola. And part D has a really long solution, and you'd never really have time to do it on the actual test. So we're just going to skip part D. I don't think it's really worth it, and I don't think you would get to it on the test. So that finishes practice test AB3. And so I will start working on the next practice test, start uploading videos for that tomorrow.